My name is Sasha. Well, the formal name is Alexander, but I mean, the first take-home message, I guess, is that Sasha is a short name from Alexander. I'm a product manager at the attocube systems, but before joining attocube, I worked many years with Rainer Hillenbrand, and of course, I was into the theory of s-SNOM. I'm a theoretician, by education at least. So this is I wanted to begin my talk with essentially kind of summarizing what was said about experiments, s-SNOM experiments. So you know our microscopes, right? So if you do things right, well, if you want to do things right in s-SNOM, you need to use our microscopes. Yeah, I had to say it because I work with the company, yeah. So, but the point here is that in our microscope we have interferometric detection. Yeah, so there's several methods you can utilize. So two of them were excessively discussed. So this is PEZ and nano-FTIR. So the idea of interferometric detection is that the signal which is measured by a detector is essentially a sum of, well, I mean, it's always not just an interferometric detection, but it's a sum of the background, near field, and the reference. The reference is important. So the detector always measures the intensity, right? So this is not the fields here, the sum of fields, but it's absolute squared. So if you do some simple algebra, so you can actually expand this square, and you get 6 terms plus 3 complex conjugates. I didn't write them down. Here's where the important part comes in. So if you do the detection, you do the phase modulation, which is essentially what PEZ and nano-FTIR are, and you do the high harmonic demodulation, yeah, together. So then what happens is that the background term is gone. So if you detect at high enough harmonic, then let's say demodulation order above 2, so normally you get the background gone. So this part, because it's not modulated by the reference, it's not modulated, I mean, the demodulation, high harmonic demodulation with respect to the tip tapping frequency essentially zeroes it. So near field term, you see it doesn't depend on the reference, which means that if you're doing the phase modulation of your reference and then you detect the signal which is somehow related to this modulation, let's say a lock-in, sidebands, or nano-FTIR when you do the full Fourier transform, then this term is also gone. This is pure reference. It doesn't have tip involved, so if you demodulate at the high harmonic demodulation again, you're applying, then this term is also gone. Near field times the background, right? So this is, well, let's say, you see it doesn't have the reference. So again, if you're demodulating with respect to the reference signal, so this one is gone. Background times reference. So again, there's no, I mean, high harmonic demodulation at high enough frequencies and above 2 is gone. And the only term is left, which is left, is essentially the product of near field times the reference. Yeah, and that's what you essentially measure in nano-FTIR and PEZ. And after the application of these techniques, what you get is essentially something which is the amplitude and the phase signals. Yeah, and here it will become important later on. So these are not the pure near field term, but it's also the product with the reference. So the signals could contain the properties of the reference beam, but we'll talk about it later. Okay, so the reason why I presented this slide and why I like this picture is because without getting into the details, I mean, this is all very nice and formal, yeah? So, but without getting into the details, you kind of understand how you can kill with these techniques, how you can kill all the background terms and actually get the pure near field. Suppose that you did things right, you use our microscope, you got a beautiful image. In this case, this is a phase image of a tobacco mosaic virus. And it's high resolution, 10 nanometer, yeah, high contrast, beautiful. But what do you actually see? Yeah? And that's kind of the question which I want to answer. For example, back in 2006, or maybe even before that, actually Fritz was here, so he's a co-author on this paper. So they did exactly this. So they imaged this tobacco mosaic virus at different wavelengths. And then from this, they extracted the spectra. Amplitude spectra, s-SNOM amplitude spectra, and the phase spectra. And what they realized is actually that the amplitude spectrum looks, well, it represents the dispersive profile of, let's say, a typical biological material. Yeah? So essentially, it kind of maps to the reflectivity of the material. Yeah? And the phase, it has the absorptive profile. You see it's kind of a peak, no? So, and essentially, it seems like the phase simply represents the absorption, right? So maybe it's as simple as when you measure something in SNOM, the amplitude gives you reflectivity, the phase gives you absorption, okay? So that's a very nice and convenient representation. So it works pretty well for tobacco mosaic virus, and as we discuss later, for many other materials. But unfortunately, well, there was another experiment even before this 2006 paper. An experiment which essentially images silicon carbide islands in gold. And what you see is, well, very nice contrast again, right? Very nice images. The problem is that it's kind of strange. I mean, gold is a noble metal, no? So it reflects pretty much everything which goes on it, at least in infrared. Yeah? But what you see is that, hey, silicon carbide somehow is more reflective. Why? Does it make sense? Yeah? And at another wavelength, it's actually much less reflective. That would make sense if everything was kind of black or dark images, but no, that's the other way around. Yeah? In fact, the reflectivity of silicon carbide, yeah, mostly for most spectral parts of the spectral range is actually much weaker than gold, but no, we see the bright spot, bright island, yeah? So something is strange here, okay? Obviously, I mean, you can't interpret it as at least a far-field reflectivity anymore. Here's another example. Okay, so this is the famous boron nitride nowadays, I guess. And you do the imaging of boron nitride, let's say at 1500 wave number. So what you see is kind of a pattern, strange pattern. What is it? A non-uniform contrast in a uniform material? Because, I mean, this, I didn't show the topography, but this is a uniform flake with a constant thickness. Yeah? But what you see is then a bunch of hot spots. Okay. What's even weirder is that if you change the wavelength, then the pattern changes. So obviously, you cannot interpret it as some kind of material contrast or reflectivity of the material, right? So because it should be uniform, you should see the same kind of uniform image. This, well, the purpose of this slide is essentially to motivate you that we need to understand what SNOM measures in order to understand our results. Yeah? And as a theoretician, I will go into the modeling. I have to say, like, put a disclaimer. So I'm not going to go into the details of a specific model. Yeah, I'm trying to be kind of on the surface and give you the guidelines and the references, so you can actually do it yourself if you want to. Yeah, but not digging too deep into the models themselves. Okay, so that brings me to essentially, well, the second point of my agenda, because I skipped the first one. I realized that there's so much stuff to talk about that I will not be able to finish it in time. So I completely removed one of the chapters, and maybe, if there's time left before lunch, I can come back to this, yeah? So, models. Again, there's so many models, there's so many different experiments. SNOM produces very rich amount of data. So I want to narrow the scope of my talk. And I narrow it essentially that the main focus of this lecture is modeling of tip-simple interaction at infrared frequencies, yeah, and for the purpose of material sciences, yeah. So we're trying to understand the material response, something like chemical component mapping and chemical identification, protein secondary structure, carrier profiling, semiconductors, phonon spectroscopy, things like this. But I will not talk about the field mapping and extraction of propagation characteristics. This will be the subject of Friday talks. So there's several people who will discuss it and, of course, talk about what you can extract from those data. So in particular, that means that I will not talk about this image, yeah, which I used for the motivation. Yeah, in fact, this is not the material contrast. You'll probably already figured it out. So Rainer briefly mentioned it, for example. So the point is that this is interference pattern of the polariton waves launched in the boron nitride material. I will not discuss this. I also will not talk about visible applications, so I will focus on the infrared range. Just for the sake of, I mean, I only have half an hour, and it's really not much time to discuss all the possible applications in spectral ranges. Okay, so the purpose, let's say, of this discussion will be not, let's say, maybe not necessarily an extraction of the permittivity, but just, let's say, understanding or making sense out of your experience and checking whether the experiment actually produces the right results. I mean, it's reasonable or it's not reasonable, things like this. So I will try to do the description of the experiment in terms of the let's say, certain assumed sample geometry. So suppose that we know what the sample roughly is, so substrate, something on it, something like this, so the geometry of the sample. And the dielectric function, it's also called dielectric permittivity of the sample material, epsilon. So it has been discussed several times already yesterday and today. So the point is that the epsilon determines complete dielectric response of your sample material, including the near field scattering. It's complex value. It is complex valued, yeah, so it has the real and imaginary parts. So, and this is a representation of it, which I stole from Reiner's slides. So this real part, so you see this dispersive profile. I don't know, I kind of tend to think about it as a butterfly. I don't know, somehow it resembles to me. It doesn't look like a butterfly at all, but whatever. So, and then this is the absorptive profile. So you see the peaks, a set of peaks. And it describes, in principle, all types of materials and phenomena like metals, semiconductors, phonons, molecular oscillators, and so on. Now, some of you might find it easier to think about the dielectric permittivity in terms of the index of refraction and the absorption coefficient. Here's the relationship for you. So they're kind of mapping almost, well, not one-to-one, but it's easy to go from one to another. Some of you probably think about conductivity instead of permittivity, also complex valued conductivity. It's kind of the same thing, essentially, yeah, and here is the relation between the two. Okay. So model, point dipole model. Again, it's been discussed for, I mean, yesterday, today also a little bit touched. So just to summarize, essentially we represent the tip as a small sphere of a radius which is much smaller than wavelength. Yeah. So and we can calculate within this model, we can calculate the scattered field. Yeah. So it's essentially proportional to some far field, or let's say indirect illumination factor. We'll get back to it later in my slides. Right now, the main purpose is that, hey, the scattered field is actually proportional to some effective polarizability, which we can calculate within this model, right? And the expression for this effective polarizability is, well, pretty simple, actually. Yeah, so it's some kind of polarizability of the bare tip. Think of the tip, no sample. Yeah, so it's this alpha 0, right? So Reiner gave this formula so for the alpha 0, so nothing fancy. The point is that it doesn't include the sample, of course. So to include the sample, you have this denominator here. So 1 minus some function f, which depends only on the tip sample distance and nothing more. It doesn't have the material response there. And the material response is contained in this factor, beta. So this factor is a near field analog of the far field Fresnel reflection coefficients. Yeah? So, but it's an analog but for evanescent waves. Yeah? Evanescent waves are the ones which are in charge of the near field interaction, and this is what so emanates from the tip and probes the sample, right? So this beta is related to the dielectric function. Yeah, real and imaginary part means that this one also is complex valued, so it has a real and imaginary part. And even if the tip polarizability, bare tip polarizability, is completely real, yeah. So and this is actually true for, let's say, metallic tips and at infrared frequencies. So this one is very large. Yeah, so you can forget about this, forget about this. The permittivity of the tip cancels out completely, so you only have some term which is proportional to the volume, radius cubed, yeah, volume of this small sphere. And it's completely real, but because beta is complex, what you immediately see is that there will be a real and imaginary part, or amplitude and phase for your effective polarizability, S and phi. And these are exactly the amplitude and phase which could be compared to the experiment. Yeah? Okay. So FDM, wrong title, point dipole. It's a simple model for quantitative analysis. It essentially approximates a large bulky tip. It's like 20 micrometer long, right? So it represents with a small dipole. Okay, fine. It's good for describing qualitatively the experiment. It has the advantage that you can extend it to multi-layer samples, relatively straightforward. But it fails to reproduce the correct distance dependence of the tip sample interaction. And this is super important. Super important because essentially it gives you a Ron approach curve. So this is kind of a schematic representation of the experimental approach curve. as you come closer to the sample, so your interaction changes, right? And there's a certain rate at which it changes and a certain, let's say, functional dependence, yeah, on the distance. But PDM, it's much more short range. This is because it's like a small dipole, yeah, and the field of a dipole, it drops down really fast, and it's gone. And this is exactly what it says. It completely misses the correct the tip sample dependence from the experiment. And that means, of course, I mean, if you do the demodulation technique, you apply demodulation, right? So you get the harmonics. This harmonics, it's essentially a Fourier series representation of the same approach curve. So if the model doesn't capture the approach curve correctly, then of course the harmonics will be wrong. And this is exactly what happens. Yeah, so here's some consequences of this. So for example, if you have materials like polymers, for example, you can see spectral shifts with respect to the experimental of the spectral features, yeah, compared to well, maybe I should step back a little bit. So this is the imaginary part of the permittivity, so essentially the absorption of the material. And what you see is that the experimental one does not match the prediction of the point dipole model. It experiences a shift. So it's not adequate for describing the spectral peak positions. Even worse, this is the example for polymer, but this is an example for so-called phononic materials, yeah, and like silicon carbide, dioxide, and so on, polar crystals. And it completely misses it in terms of the magnitude of the response and also in terms of the peak position, yeah, and even the line shape. I mean, it's not even comparable, right? So this is experiment, this is PDM. Yeah, but qualitatively, it could still provide certain phenomenological description. But we want to do better than that. So let's try to figure out why point dipole fails. So obviously, I mean, we have a big, bulky metallic tip, and we represent it with a really small dipole over there. Yeah, and that's basically the reason. So for the real tip, when you illuminate the tip, then it produces a very strong polarization. Strong effective dipole here, much stronger than a small particle. And because this dipole is much longer, that leads to a much larger separation between, let's say, the opposite charges. Yeah, the tip is still neutral, right? So, but you have the polarization, which means that you have some charges here, but the compensating charges are really far away, yeah, in the tip. They're distributed along the tip far away. And that means that your sample here in this probing volume, small probing volume, the sample is actually probed by just the charge, not the dipole, but the charge, right? And of course, you know, I mean, the field of a charge decays 1 over distance squared, and the dipole is 1 over distance cubed. And that's exactly the reason why point dipole fails, because, yeah, it doesn't capture the correct distance dependence. In fact, what happens, let's say, in the proper description is that the sample is subject to this monopole field, or field of a charge, and there was an attempt of, let's say, calculating the response of an s-SNOM by trying to represent the tip as the scattering of a realistic tip. And so this is the essence of a so-called finite dipole model, which essentially represents the tip with a conductive, relatively large conductive spheroid. So what happens if you take the spheroid, suppose that, forget about the sample for a moment, yeah? So you take a spheroid, you illuminate it with a field, it polarizes. And there's analytical expressions, you can calculate how much it polarizes. So the point here is that the polarization of the spheroid could be expressed in terms of 2 opposite charges. I call them Q0, yeah? So one charge, opposite charge. And these charges form a relatively large dipole. So the dipole is what? Charge times the distance between the charges. So it's 2Q0L. So, well, L is some kind of size or length of the dipole. Okay, so far so good. Now we put the sample in. What happens? You have a charge and now this charge starts interacting with itself through the sample, right? So think of it this way. So I kind of zoomed in. Let's forget about these charges. They're presumably far away, so they don't participate in the near-field interaction. So, but what happens is that you take the charge, yeah? It forms an image charge here. Yeah, this image charge is then forming an image charge in the spheroid, right? And here, where the problem comes, actually, it doesn't map, this charge doesn't map into the same location and the same magnitude, yeah? But actually, what happens is that there is a distribution of the induced charge because of the interaction with the sample, not like a point, but it's a distribution along the axis of the spheroid. Yeah? And in principle, I mean, you can calculate it, but that would be quite complicated because this distribution depends on the tip sample distance. So here's where the approximation is made. So the approximation says, well, you see this charge peaks at a certain point, and this point is approximately the focus of the spheroid. So we represent this whole charge distribution with some kind of effective induced charge, and we place it at that location, okay? So essentially, now you're saying that in the presence of the sample, there's two charges in the spheroid, in our tip. One of them is this Q0, which is the initial polarization, and the second one is the induced because of the interaction, and it forms an additional dipole, and this dipole radiates to the detector, okay? And this is the radiation which we're interested in, and this is something which tells us about the properties of the sample. So, not going into the details, so we write down this radiation in terms of, well, in similar form. So scattered field is proportional to some far field or indirect illumination factor, then effective polarizability, and here's the formula for the effective polarizability. So you see, it resembles the dipole model to some extent, right? So this is your alpha 0, that's just the polarization of the tip without the sample whatsoever, and it has a contribution, additional contribution, which comes from the near-field interaction. This contribution has, let's say, two distance-dependent functions. So just like with the dipole model, I mean, you can find the expressions for these functions here in the original paper. The point is that this is just the distance dependence with some, let's say, model parameters, yeah? And then there's explicitly here, there's again this beta factor, which is the quasi-static reflection from the sample, yeah? And this is what we're interested in. So relatively simple model. So far, so good. So what happens is, I mean, it was, if you take these expressions, you plug in the numbers, then suddenly, so the prediction of the finite dipole model matches really well with the experimental results. Yeah? And that's the advantage of this model. So if it matches, that means that you get the harmonics right. And if the harmonics are right, you can actually quantitatively compare to your experiment, right? And in principle, extract the parameters of the dielectric function, the quasi-static reflectivity, and so on. Okay. So the advantages of the, I mean, this is actually the proof that it works, right? So these points here, this is the experiment on the silicon carbide, and the line, the red line, is the prediction of the FDM, and you see it's an extremely good match, especially if you compare it to the prediction of the point dipole or some extensions of the point dipole models. So the model has only two parameters, two free parameters. Yeah? One of them is the effective length of the spheroid, yeah? And the second one is a so-called a fraction of the induced charge which participates in the near-field interaction. So let me maybe go one step back, two steps back, and explain what I mean. Remember, this is an effective charge. It's not the full charge induced along the spheroid because a lot of it is outside of the near-field zone. So, but it's an effective charge. And essentially, this parameter G tells you, oh, okay, so it's not the full induced charge, but only 70% actually, which participates in the near-field interaction. The way we find these parameters is the following. You take some kind of known test sample, right? So with dielectric function. And then you do the experiment. You measure with specific tapping amplitude and so on. And then you try to match the values which you get in the experiment with your simulation, yeah, with your theoretical model. And if you do this, because you know the sample parameters, you know the sample properties in this case, you can actually find what are the effective lengths and what is this fractional charge which participates in the near-field interaction. And that was done, this is exactly what was done by, I think, Nenad Celic, if I'm pronouncing that correctly. Yeah?
What about W0, WY, and Q?
These are calculated. Within the model, they're not fitted, they're calculated, so you can get analytical expressions. Yeah? So WI is actually, this is the focus, so that's the focal distance of the spheroid. W0 in the approximation, I think it's something like 1.38 times the radius of the curvature. Okay? So the real fitting parameters, there's only two, these two, that's it. One peculiar aspect, I guess. So you see this G, the fractional charge, it actually has an imaginary part, yeah, which is to some extent weird, but then that means essentially that even if you have a completely non-absorbing sample, you will still have a little bit of the phase in your images, yeah, if you do the model calculations. And the reason for that is that, well, it doesn't relate to the sample absorption, but actually it's something which is an absorption by the tip to some extent. Well, it's called radiation damping, because in principle the tip does not have ohmic losses, so it doesn't absorb in the sense of it's dissipating the radiation into the dissipating into the heat, but it absorbs in the sense that it creates the field and then it interacts with that field, yeah, and that creates a so-called radiation damping. So this is what it accounts for. So in fact, you can even say that maybe there's 3 fitting parameters. So there's this imaginary part, which is relatively small. There's this fractional charge, percentages, 70% in this case it was found. And then the effective length of the spheroid, which in the model, so Nenad figured out that, well, it fits the best for the majority of tips with 300 nanometer length of the, well, half length of the spheroid. Which is, again, I mean, you have a 20 micron tip, but again, the effective spheroid is only, what, 600 nanometers? Much smaller still, yeah? But still, the model is very good in describing the experimental data as shown here. Now, to be, let's say, on a practical aspect, so if those of you who want to do the simulations themselves, yeah? So you want to verify whether you're doing it right or not. Maybe there's a bug in your code, yeah? So here's what you can do. You can take this model parameters, so gold, silicon, tapping amplitude 16 nanometers, tip radius, you assume 25 nanometers. And you plug it into your code of the monopole model. And you should get these values for the second harmonic, the ratio between the second harmonic scattering on silicon to gold. 0.61, 0.55. These are the kind of the reference values. I always do it if I write the code from scratch. I check whether I get the right values. Ta-da. So for the reference, if you want to try with the dipole model, you can also do this. You should get these values. If you don't get these values, then you're doing something wrong. So you need to search for a bug in your code. If you get it, you're good. You can continue. You can extend. That means that the demodulation works and everything there. OK, now the problem, well, not a problem, but strictly speaking, finite dipole model is developed only for, it's only valid for bulk medium. So in other words, we assume that there's no layers. It's just one semi-infinite medium. And most interesting samples, I mean, in many cases it works. It works pretty nicely, let's say, for thickness of materials which are on a scale of 100 nanometers, right? So if it's above that, so the near field doesn't sense the substrate, you're fine. But in many cases, you have much thinner films. I don't know, 10 nanometer film, 20 nanometer film on top of your silicon substrate, yeah, or some kind of nanoparticle. Well, that's a separate subject, but let's say, suppose that it's something relatively thin, yeah? So how do you use it? How do you make sense out of your results? So, and there was another model developed, or essentially extension of the finite dipole model done by Benedikt Hauer from the group of Thomas Taubner. And what it does is the following. It's a simple modification of the FDM. So what you do is you say, well, FDM works with the quasi-static reflection and, let's say, certain position of the charge which is calculated in the model. Now, if you have a layer, let's use the same model, the same expression, but, well, we replace the actual beta and the actual position of the, let's say, image charge in the model with some kind of effective parameters. And these effective parameters are chosen in such a way that they represent the effective response of this layered medium. Yeah? And the cool thing is that, well, Benedikt essentially calculated these effective parameters, yeah? And these are the expressions. Again, you can go to the paper and you will get the full formulas. Yeah, I just wrote it down, let's say, in a general form. The point is that they express through a so-called electric potential. Yeah, and well, the assumption in the model is that, well, you want to have these effective parameters calculated in such a way that they represent the correct field of this of the image charge at the location of the original charge. Might sound a bit cryptic, but I mean, if you get into the details of the paper and you really want to utilize the model, then you'll understand what I'm talking about. Essentially, that's an extension to multi-layers, and it has a lot of advantages, so it really describes the multi-layers. It's relatively simple. Thank you. And it works well for polymers and biological matter. Yeah? So the disadvantages, or something which you should know, the model has not been tested on polar materials, so you can try, yeah, but in my experience, it didn't actually work. Yeah? It doesn't work for polar materials, for strong oscillators. And the reason for that is because, well, The possible reason is that we don't account for the screening. So if you have something which is very strong, yeah, so you put it as a layer, it screens the substrate, and then the model doesn't apply. Okay, so I'll skip this since I don't have much time, so I have to put it on a slide because it's my work. So it's so-called perturbative approach. The idea is that you try to represent the tip sample interaction as some kind of series of interactions. Let's say in this case, I try to represent it as like you have a tip and interacts with a substrate, then the tip interacting with the, let's say, semi-infinite medium, and then you need to subtract something because, I mean, in reality, you only have a layer and not the semi-infinite medium, right? So it's kind of this plus this minus that, and that would be the first perturbation order, which actually is not bad in describing certain dielectrics. You can go to the second order, third order, and so on. And the cool thing about it is that you can utilize well-established bulk models, and you essentially extend them to the multi-layer. Yeah? There's a couple more advantages, yeah, but certain drawbacks. This also approach, I doubt that it could work for phonons, for example, because the perturbation breaks down there. All right. This is probably the most advanced model. It's called lightning rod model. That's the most advanced model probably in existence to some extent. And what it does is essentially it calculates a so-called T-matrix for the tip. You can digitize the tip. You can calculate numerically, like crunch the numbers. So it requires quite some computing power, let's say. But you can calculate an arbitrary geometry. And then with this T-matrix, once you have it, you can calculate the interaction between the tip and your sample. Yeah? And then you can, again, do this iterative or fitting approach to extract the effective beta and then relate it to the real and imaginary part of permittivities. So the cool thing about this model is that there's no fitting parameters. You don't fit anything. You just take the real tip, digitize it, calculate. Yeah? And it can reproduce absolute values of the field enhancement, for example. So I told you, remember, so the dipole length, effective dipole length, and the finite dipole model is something on a scale of 300, 600 nanometers, right? But the real tip is 20 nanometers. So if you try to calculate the absolute fields with that model, you probably will fail. Yeah? So it's good for contrasts between the materials, but it doesn't reproduce the realistic field enhancement because, I mean, it still considers the tip to be relatively small. This one can get you the right results, including the field enhancement under the tip. But of course, let's say the drawback is that it's numerically intense, and even writing down the code is quite complex. Reference table. I try to summarize, let's say, different models and put the references. Yeah? So I already mentioned, I mean, Rainer actually mentioned point dipole, so you can find it in their book chapter with Fritz. So finite dipole model, so this is the reference. Quasi-analytic model, that's Benedict, and several more. Actually, Lars is one of those who developed another extension of it. So then perturbative, so there's a couple papers from my works. So then numerical approach, that's essentially the lightning rod. Then there's a couple more which I didn't mention on the slides explicitly, but these are very interesting. So calibration-based. So sometimes you actually don't have to go deep into the interaction model itself, but you can actually extract your permittivity, for example, by calibration. You do some set of measurements on a known sample, you get certain model parameters out of that, and there you go. And then machine learning. It was briefly mentioned yesterday already, so that's an interesting approach, but it's very young, so let's see where it goes and if it's possible to do, I mean, how util it is. All right, maybe quickly. So there's a class of materials which are called weak oscillators, or we refer to them as weak oscillators. So polymers, biomaterials, and so on. So the dielectric function for this material doesn't drop below zero, right? So these are molecular oscillators. And so what you can show that whatever model you take, point dipole model or finite dipole model, so they all have this factor 1 over 1 minus f times beta, right? So, and beta for weak oscillators is actually below 1. So let's do a Taylor expansion. The first two terms is 1 plus f times beta, okay? So you put it into, let's say, point dipole or finite dipole. What you see is that apart from this constant offset term here or there, your alpha effective is proportional to beta. So essentially what you're measuring is the quasi-static reflection coefficient, yeah? Not in magnitude, of course, but qualitatively, yeah? Spectral response, for example. And in particular, you can say that, hey, you can define a so-called non-FTR absorption, the imaginary part of your scattering coefficient, for example, and it will be proportional to the imaginary part of beta, and that one could be related to the absorption coefficient. And this is actually the basis why why what you see in these images is indeed could be interpreted as the reflectivity and absorption. But that only is true for the weak oscillators. Now, yes, it is true for weak oscillators, and it's a good thing because it's actually a really large class of materials, polymers, biomatter, and so on. And that gives you an ability to do a spectroscopic identification of the chemical composition of the material, because you can do the spectroscopy on the material and then compare one-to-one with some far-field databases. Yeah? So this is a representation. So far-field FTIR, let's say transmission, and then ta-dam, the peak positions, yeah, the reflectivity, so profile is the same. So you just put it into the database and, aha, this is my PMMA, this is my polycarbonate, and so on. Okay, now this is the problem, where the problem comes in. The same interpretation of reflectivity and absorption doesn't really work for crystals, yeah, for semiconductors, for metals around resonances, and so on. And this is exactly what was represented in this example, which I showed you earlier. So in this case, you cannot do the scalar expansion just because the beta is resonant, as Rainer pointed out yesterday. Yeah, beta is resonant, which means that you cannot relate the imaginary part of the effective polarizability to the imaginary part of beta. It doesn't work anymore. In fact, what happens, again, schematically, is that your spectral profile of the, let's say, nano-FTIR is related to the resonances, phonon or plasmon, depending on which material you're looking at. Yeah? So it relates to the resonance of beta. So essentially, when epsilon is around -1, beta blows up, it becomes large, right? And this actually defines a so-called a low phonon frequency for polar crystals. And what happens is that in such materials, you can get the resonance of the tip sample interaction. It's actually not the resonance of beta, but it's the resonance of the tip sample interaction expressed by the effective polarizability. So it's when F times beta is around 1. Okay? The exact position, I mean, qualitatively describes the picture, but the exact position of the resonance, you actually, in order to find it, you actually need to do the demodulation, plug in the numbers, mimic experimental parameters like the tapping amplitude, it's actually important, and the tip size, and then you get the spectral peak. The good thing about it, I mean, on one hand, it seems complicated, but on the other hand, established models, finite dipole model, actually gives you an ability of calculating this response and get the correct positions, and in principle, extract the dielectric function. Okay, so this is schematic representation of what you do for polar crystals. Yeah, you assume certain dielectric function model, so in this case, Drude. So you calculate the near-field reflection, you calculate then the effective polarizability, right? Do the demodulation, and compare the results to the experimental data, right? If it fits, excellent. If not, then you adjust the models and the dielectric function, yeah, and repeat the whole process until you have a good match with your experiment. Yeah? So that's the idea. Okay, now that requires comparison to the experiment, yeah, and that brings me to the last part of my talk. So how do you compare to the experiment? First thing you need to do with your experimental data is to do the reference, the normalization, right? Because Rainer pointed out that s-SNOM doesn't give you the absolute measurement, right? So it gives you the measurement, and you need to relate it to something, because phase, for example, otherwise is not defined. It's defined with respect to something. So you can define it with respect to the phase of your beam in the reference arm of the interferometer, but do you know what it is? No. So what you do is you take a second measurement normally, and you normalize the data in a complex way. That's important, complex way. Yeah? So the amplitudes are essentially, it's the ratio on your sample to the scattering amplitude on the reference material, but for the phases, it's the difference. Okay? And this quantity, this ratio, is often referred to as a near-field contrast. Okay? It's always defined with respect to something, which means that the actual value, for example, the peak height, depends on what is your reference material. If you do the measurements on silicon, that's one ratio. I mean, that's one value. If you do it on calcium fluoride, it will be a different ratio, right? You have to keep it in mind, yeah? So you have to make sure that you know what the reference is, and when you calculate, you take the dielectric function for the reference there for the calculation. Okay, now demodulation. That's kind of a scary word, and it involves an integral. And of course, if you're good in math, you can go ahead and do this, yeah? Or you can use a program like Mathematica, it can also do it. But strictly speaking, hey, it's kind of, yeah, a complicated thing. So what I wanted to do, I wanted to give you a practical recipe how to do the demodulation without doing complicated mathematics. In fact, all you need is the DFT. So demodulation, you have the tip tapping, you take this, let's say you take this tip tapping and you need to plug it into the effective polarizability that gives you the time trace of your near field signal, and then you do the Fourier series expansion you get the harmonics. Okay? Yeah, you can do it like this mathematically, formally, nicely, but actually, I mean, this integral, Fourier integral, the calculation could take a while. Especially if you have a lot of points, yeah? And you do a lot of fitting and iterations and so on. So instead of doing this, what you can do is the following. You take one cycle of the tip oscillation, you digitize it, yeah? So with a certain number of points, so it's a cosine dependence, let's say, yeah? So you take, I don't know, some n number of points, and then you digitize it. So at the end, you get the array of your tip positions as a function of time over one cycle. You take this, you calculate the corresponding array for the effective polarizability. It's a time trace. It essentially gives you sets of points along one cycle, how your near-field response looks like. And then you take this and do the DFT or FFT, whatever. If this is, yeah. Normally in modern libraries, this is done automatically with FFT. But the point is, then after that, you get an array, which is FFT of your original data set. And the interesting thing is that the numbers which you get in this array, yeah, the 0th number is exactly the 0th order, the DC. 1 is the first order. The second element would be, sorry, the second position would be the first order, third, and so on and so on and so on. Okay? It works like you're done. You can do it in real time with your data in principle, yeah? Which is the cool thing about it. And also practical guidelines for n equals 32, you're already, it's sufficient. So it's really a small number of points, at least when you're working with, let's say, harmonics below 5. Yeah, so more harmonics you have, the larger array you need. So I'm not going to get into the details. And also question to the audience, you don't have to answer now, but think about it. So you see this 1, 2, 3, and so on. But there's also the components in this array which are kind of -1 from the first one from the end, second one from the end, and so on. So it's interesting to think what these are. So, but we're not going to talk about it now. So comparison to the experiment, indirect illumination, very important. So the indirect illumination is something which outside of the near-field model, yeah? And you need to make sure that you properly account for it, right? So you set up the experiment in such a way that you know how to calculate this, or you set up an experiment, and the best way, of course, is to set up the experiment in such a way that it cancels out. Yeah, Rainer showed you yesterday several cases when it does cancel out completely, and then you don't have to worry about it much. Yeah, but you need to be aware that it exists. So some practical guidelines: keep the sample and the reference point close. Yeah, so. Avoid partial illumination, and so on. But what I wanted to maybe briefly mention, and I think Lars will go into the details of this, is actually there's post-processing solutions. One of them is normalization of one harmonic to another harmonic, and that cancels out because it's at the same spot, the same location. The indirect illumination cancels out because it's exactly the same for both harmonics. There's also a solution from NearSpec. Fritz, just for you, you actually raised this question, so I decided to briefly add a slide there. There is a possibility of using lower harmonics in order to compensate for interferometric drift and actually provide this normalization on the spot. Very similar to what Lars will talk about, so the normalization of one harmonic to another. But think about it. So if you take, let's say, even the first harmonic, you still have the near-field response on it. So when you normalize, let's say phase, you're subtracting something, so you're decreasing your contrast. And sometimes it becomes below the signal to noise, below your noise level. So it is beneficial to actually use an approach which was developed actually at NearSpec. So you can calculate the reference phase, which is essentially the phase of the background, kind of, you can think about it as gating. So you cut off the part of your interaction when the tip is close and only look at what happens when it's far away in the oscillation cycle. And that is, this provides a reference, and you see this reference is almost flat, but it contains all the noise. This is really noisy data, so don't take it as a reference. Our microscopes are much better. But this is more of a very noisy image, data in a cryo system, yeah, of the first generation, let's say, and under really bad conditions. Yeah, so it's essentially a test for how well the self-reference works. So with this, I essentially would like to stop and pass the word to Lars. Do we have time for questions, or shall we leave it
Yes,
later?
thank you very much, Sasha. We still take questions, please. Yes, Vladimir.
Thank you. I have two questions. One thing about this finite dipole model, you have these two parameters which you find from by comparing to experiments. Is there any wavelength dependence of these parameters like length and G?
Yes and no. So it depends on the spectral range. So if you go from IR to terahertz, then yes, there's a dependence. You need to adjust that. If you're interested only, let's say, in mid-infrared, then you can use one set of parameters and there's no dependence. You can neglect this. It's flat, more or less.
Okay, and another question, like you rely on this approach or retraction curve and by comparing to experiment. But in fact, in experiment, you don't measure the pure near field. You measure high harmonics. What should you do?
You can still measure the approach curve demodulated. Yeah, that's true. I kind of mixed two things together just for the sake of simplicity, and I really like that you picked it up. So I was expecting somebody to do this. Let's put it this way. You still, in order to mimic the experimental approach curve, yeah, you still need to calculate the full approach curve without demodulation, and then assume that you demodulate, right? And if the model captures one right, so it will capture the other right. So, but they're not the same, that's true. There's a distinction.
Two questions. So first of all, about indirect coefficient C. So could you provide some ideas how it could be estimated theoretically? Why it's so far from 1, for example?
Yeah. So for this, I'd like to refer you to the original, well, actually to the thesis of the guy who developed the model. So Nenad. So I can give you the reference later on. So he has a discussion, a chapter which discusses this C, this indirect illumination. So how it relates, you can, in principle, if you know your sample, you can try to calculate this. It also has the polarization factors involved and so on. So it's a relatively long discussion, and it's kind of untouched to some extent, yeah. But you can look there, and then, I guess, develop on your own further, because most people just kind of ignore it or try to compensate it.
Okay, thank you. And second question about finite dipole model and the coefficient G, which has imaginary path. And I heard several times that it's related to radiation damping, but I cannot say that I'm completely believed in that, because it's look so high for the radiation damping, because the system is really small, much smaller than the wavelengths, and it's hard to believe that it leads to such high
yes,
damping.
and we can discuss this, but the system, I mean, the parameter is chosen in such a way that it represents the radiation of a big system. And this is why you need to introduce it ad hoc, because, yeah, in the model it is a small one. You know what I mean? Yeah.
Okay, I would like to add to the question you just asked, whether at long wavelengths you have a different L coming out, but you didn't say how different is it? Is it
so from my experience, if you go to terahertz, let's say something on a scale of, I don't know, it was, I think, 200 micrometer wavelength or something like that. So it doubles.
It doubles from half a micron to 1 micron.
1.2
so my basic
question
is there a physical understanding of the quantity, a micronish sort of size for that extended dipole to interpret things? It's not the wavelengths, it's much smaller, it's not the tip size. What is it? Because I want some plausibility.
How about we get together later, I don't know, for coffee, and we discuss? Because it's a good question, yeah?
We have a question here.
Okay, thank you. Thank you for the talk. It was very wonderful, and I like to see a lot of models because I also work with them. My question comes in a practical way. So, for example, let's take a model. Doesn't matter what. You just calculate the near-field interaction between the tip and the sample at certain tip height. So, from 1 nanometer to 50 nanometers. So, you have to select a good enough number of points, then you have to interpolate that, and then you can, for example, interpolate with a linear interpolation, polynomial interpolation, spline interpolation. Then you have to demodulate that, and then you have to choose different packages for the modulation. So you have a lot of uncertainties there, and then that's, I mean, you can have like different ways to process the data or to demodulate the data. And then that surprised me when you do this with this model and this dielectric function, you get this number. So do you have any estimation of the uncertainties that you can make depending on the interpolation, the amount of data you collect, or the demodulation you do?
Mm-hmm. I don't think there's an uncertainty in terms of the computation itself. I mean, it's relatively simple in the sense that, really, you take a sign, you digitize the points, you plug it into the model. The uncertainty, the majority of it, comes actually from the experimental data. And then, of course, depends on the quality of your data. Yeah, you can get it better or worse in terms of the estimation of the model parameters, like the dielectric function.
Last question here, sorry.
Okay. We can talk. I mean, I'm not going anywhere. So.
Thank you for the nice talk. Quick question. So instead of using beta, can you use the Fresnel reflection factor for the given in-plane momentum for the dominating near-field component?
Okay, then I guess the answer is yes. In principle, you can represent it. It works pretty well for graphene. You can find the effective plane wave momentum, for which you need to calculate the Fresnel coefficient, and then you can describe your peak position at least. Yeah, this is possible.
Okay, I know not all questions are answered here, but please take the chance and actually during the lunch break later to talk to Sasha. Thanks, Sasha, to you.
Or dinner time. I'm all yours. Thank you.